Today, we're going to finish up chapter 1 and then move on to chapter 2 and really kind of start the story, if you will, of atoms and elements. Yeah?
When's the chapter 1 number?
Okay, so chapter 1 homework unofficially is due a week from today, shall we say. I won't be checking it or anything. I won't collect scores until midterm to see if you've actually done it. So it's kind of up to you to do it, I guess, if that makes sense. The only times it really comes into effect is when I'm calculating like an overall grade. So you can keep that in mind, but it is useful to do it before the exam and so forth. So keep that in mind. I don't think the exam's for at least a couple weeks. 3 weeks maybe, something like that. So. Okay, so unofficially, a week from today, because we're finishing the chapter, officially the end of the term is your last chance to do it. Yeah?
When will chapter 2 notes be available?
Okay, so chapter 2 notes will be available today.
Okay.
Yeah, today I'll be able to. My plan is to always have them done ahead of time for you before we get to the chapter, but that's my plan. I'm sure you understand that. So there you go. You guys, I assume you all like having, I guess it doesn't matter. If you don't like having the notes ahead of time, just don't look at them. So there we go. Anything else? Everything else make any sense with the class? General, normal, kind of. I know for some of you it's been relatively boring reviewing things and so on. In the next chapter we'll get into a few things that are relatively new, I would bet, for most of you. So bear with me. Okay, to get our minds going today, I thought I dropped my marker. I thought we would do a density problem to get started. Last time we talked about density and we talked about the formula for density, which is density is equal to mass over volume. Now, generally, volume is in milliliters. One thing you probably should be aware of, just for your own general knowledge, I'll always answer this if you ask me about it, but centimeters cubed, cm to the third, is the same thing as a milliliter. So they're completely interchangeable in the metric system. That's actually the definition of a milliliter. It's a centimeters cubed. So if you're familiar with the nursing profession or doctors at all, they talk about cc's. Give the patient 3 cc's. A cc is a cubic centimeter, which is then the same thing as a milliliter. So 3 cc's is the same thing as 3 milliliters. And they're interchangeable there. Nowadays, on syringes, they're switching up to milliliters because that's more of the official volume. However, you'll still see them with cc's on it from time to time. My mother-in-law is a nurse, and she always refers to them as cc's. So that's where it is. So here, we've got grams per cc or grams per milliliter as our unit. So let's say, for example, what volume would 50 grams of aluminum? Okay. So if we had 50 grams of aluminum, what volume would that be? And just because we talked about it last time, let's figure this out in 2 units. The first unit being milliliters, or again cc's, and the second one being liters. All right, so see if you can find the answer in milliliters, and then after you have that answer, you feel good with that, see if you can calculate what it would be in liters. say 30 seconds or so. Okay, does everyone have their ideas down? Even if you didn't get all the way through it, you'll know whether you're on the right path or not. Really, this class and a lot of the math in this class is about taking the right steps and so forth, not the actual answer. I don't particularly care what the volume would be on a personal level. But I do care that you kind of think about it and figure out the steps. So, what would the volume be? So we want to solve for volume. So volume is going to be equal to mass divided by density. So here then is going to be 50 grams divided by the density of aluminum, which is 2.7 grams per milliliter. Now here, unit analysis will actually help us out with this. So here we've got grams over grams. So those are going to cancel each other out. So in density, you can use the unit analysis approach to actually confirm you set up the problem correctly by looking at your units. So what that means is now we've got milliliters, which is the denominator of the denominator. It's really fancy words to say you just move it back on top. And that's the unit for volume we're looking for. So that's great shape. So then it's just a matter of the math. So 50. I keep hitting this button like something's going to happen. Battery's dead. 50 divided by 2.7, I get 18 and a half. 18.5 milliliters. Okay, does everyone agree with that? Any questions? Yeah.
Where did you get 50 from?
The 50?
Yeah.
From the problem.
Oh, okay.
What would the volume of 50? So that's where that's coming from. Any other questions? Okay, so that is what it is in milliliters. So the next part of the problem is to try and convert that to liters. So if we're going to do that, we're going to start with 18.5 milliliters. And over here, we're going to put liters. And we need the relationship between milliliters and liters. So is milliliters going to go above the line or below the line?
Below.
Below the line. And liters is going to go on top, so that way milliliters cancel, liters match. And we just have to put in our number. So for every 1 liter, how many milliliters are there? 1,000. 1,000. So 18.5 times 1 is going to be 18.5. Divided by 1,000 is going to be 0.0185 liters. 0.0185 liters. Does that make sense for everyone? Following along with the steps? And so I like this problem because first it shows that you can look at the units to cancel out and make sense of density. And then second, it's got a metric conversion thrown in too. I'm going to say for fun. Probably not for all. Good there? Seem to have a grasp of density? Moving on? Going? Good. Always think of like an auction unit. Okay, so a few things just to summarize density. Density, if you remember what we said last time, is the ratio of the mass to the volume. Now what that means is just how much stuff is crammed into a volume. Okay? The more stuff that's crammed into a certain volume, the higher the density is going to be. And in chemistry, when we think about that, it's not just stuff, it's atoms. So the more atoms that are stuffed into a volume, the higher the density is going to be. And the bigger the atom, or the more dense the atom is, then the denser something's going to be. So for example, gold is AU on the periodic table here. Number 79. Aluminum is number 13. So even if they had the same compactness, there's a lot more to a gold atom than there is an aluminum atom. And because there's a lot more to that atom, it ends up with a higher density. So we'll see how that plays out in the next chapter a little bit. When we're looking at phases of matter, gases are the least dense, then liquids, then solids. And this is one of the reasons why most solids sink when you put it in with a liquid. One of the very, very few exceptions to this rule is ice, which is amazing because if ice wasn't that way, we wouldn't be here. The world wouldn't exist as it normally does if it was any other way. But most of the time, when you go to the solid phase, it's more dense than the liquid phase. So what does that tell us about atoms themselves? In comparing a gas and a solid, which one is going to have the atoms more tightly packed together? The solid will. The solid will, because it's denser. And we know that too by looking at the atoms and so forth in a variety of ways. That's absolutely true. And liquids are in the middle. So in gases, atoms are far apart from one another. In liquids, they're relatively close to each other, but not tightly packed. And then solids, they're completely tightly packed together. And this also explains the behavior. Why gases fill a volume, because the atoms can move as far as they want to. Liquids will change shapes because they're not locked into place. And then solids hold those shapes because the atoms are actually locked into place. And we'll talk about that numerous times through the course. Both liquids and solids can have a variety of densities depending on what they're made out of, the temperatures and so forth. And then liquids, gases, the temperatures will affect the density. Okay? Temperature does affect density in a solid, but it's very, very small compared to other things. We see this in balloons a lot. Okay, so if you have a balloon which has got a gas inside of it, and you make it really, really cold, what happens to the balloon? Okay, it shrinks. It shrinks down when you make it cold. And that's because you're changing the overall energy of the atoms, and the density gets larger. Which is a good segue into the last topic for this chapter, and that's temperature. So temperature in this course is going to be the motion of atoms. The larger the temperature, the quicker the atoms are moving, right? And the further the distances they're moving. The lower the temperature, the less the atoms are moving, and the slower they're moving for one another. So right now we haven't really talked much about what this means, and we will in a little while, but just accept the fact that the higher the temperature, the more atoms are moving. The lower the temperature, the less the atoms are moving from one another. Now to describe temperature, we have three different systems. We have the Celsius system, the Fahrenheit, and the Kelvin, and then we've got conversions between them. These are not conversions that I want you to memorize, but I would like you to be able to work with them. So if I give you a temperature in Fahrenheit, you should be able to convert to Celsius. If I give you a temperature in Celsius, you should be able to convert to Fahrenheit or to Kelvin, whatever we need to. We can try a couple of these. So for example, what is the Kelvin? Let's see. Oh, that wording is bad, but temperature of 300 degrees C. So when we're doing this, it's just a matter of plugging the numbers into the equation. And we look up there, and we see that degrees C minus 273 is Kelvin. That's not right. 300. Oh. should be plus. Plus 273, not minus. Plus, because Celsius is always higher. So it's got to be a plus. We're making that change. Sorry about that. Okay, so we're just going to plug it in. 300 plus 273 is then going to be 573 Kelvin. And that's how that will work out. Let's try another one. If I mess that up somehow.
Wait, quick question.
Yeah.
So that means it's 570 degrees up? I don't get that part.
So 573 Kelvin is just the same as saying 82 degrees Fahrenheit.
Okay. Is there any way you can convert that, or you just keep that the same?
You can convert it to Fahrenheit or to Celsius, if that's what you're asking about. Kelvin is just what's used by the scientists for temperature, but we can absolutely convert that to something else. Let's say, for example, what would the Celsius, degrees Celsius, be of 200 Kelvin? Okay, so what would degrees Celsius be of 200 Kelvin? So see if you can figure out what that would be using the correct plus there instead of minus. Just as a reminder. So degree C plus 273 is equal to Kelvin.
How much Kelvin is that? 200?
273. Oh, sorry, 200. Okay. To solve this one, then we're going to put the 200 in for the Kelvin. So degree C plus 273 is equal to 200. Subtract 273 from both sides. And degree C is equal to negative 73. So negative 73 degrees Celsius. Okay with that? That one's relatively easy, assuming I give you the right formula, because you're just adding and subtracting the 273. The other one, the Celsius to Fahrenheit, unfortunately is not quite as tidy. The formula for that one, I hope I got this one right. C times 1.8 plus 32 is equal to Fahrenheit. So let's check this one with something I know. What is the Fahrenheit, degrees Fahrenheit of 100 degrees C? Yeah. Typing away, so we'll give them another couple seconds, few seconds. Okay. So to do this one, again, we'll just plug the number in. 100 times 1.8 plus 32 is equal to degrees Fahrenheit. So 100 times 1.8 is 180 plus 32. Add those together, you end up with 112 degrees Fahrenheit. Oh, 212. Thank you, 212. 212 degrees Fahrenheit. Anyone have any idea why I would actually know that one? Why 100 degrees is equal to 212 is of importance?
Boiling point of water.
Boiling point of water. Yep. Water boils at 100 degrees Celsius, which is 212 Fahrenheit. Another reason non-metric doesn't make much sense. Okay. Questions about that? I don't really want, like, I'm not trying to trip you up or anything. I'm just going to give you a problem like this to say, can you convert? Here's the formula, can you convert? Something like that. Okay. Okay. So once we understand temperature a little bit, we can talk about what's called the kinetic theory of atoms. Now, I'm a little hesitant to talk about this at this point, but we've talked about atoms, we've talked about temperature and so forth, and you understand what motion is. So this is the formal explanation of atoms moving as a function of temperature. And what it says is the higher the temperature, the more forces the atoms can overcome and move further apart. So just think of it this way. The higher the temperature, the more energy is in the atoms, and they move further apart from one another. That's really the basic of the kinetic theory of atoms. It doesn't sound like much, but when you think about it throughout this course, we're going to see time and time again how this can actually be used to interpret everyday events. So for example, balloons. You know what, if I remember right, I'll bring down balloons next time and we can do this as a demonstration. You make a balloon, you blow it up in the air, and then you put it in dry ice or liquid nitrogen or something very cold, and it shrinks way down. The reason for that is because when it's cold, the atoms inside the gas have less energy, so they can't force the balloon apart as much. And that's why they shrink down. As it heats back up, the balloon gets bigger because you're putting energy back into the atoms, and then it can push on the sides, and then it forces it open more and more. This is the same with the phase changes from solids to liquids to gases. As you cool down energy, or actually solids, liquids to gases would be increasing energy. You put energy in, and these atoms, which are locked together, can then break apart a little bit and then break apart more and more, and that's when we see the phases. So this really is an underlying theory, and we're not going to work with it a whole lot now, but I want to introduce it because this is the time to do that. Have you guys heard of the kinetic theory before? The basics of it, maybe not called that, but like atoms moving as a function of temperature and so forth. There's a lot of examples of it. The easiest ones to kind of see are the expanding as you heat stuff up. So as, like a marshmallow. Oh, that's not a marshmallow. If you can heat up the inside of a marshmallow without melting it, it actually will expand out because the gases get bigger and bigger and they expand. Soap is another one. Cake. Cake. When you're making a cake, why does the cake rise? Gases are being created, and then they're being heated, and then they're expanding outwards. So you start seeing your cake. And whenever I make a cake, it's always too much, and then it gets all over the place. Just a little bit does you. You guys probably don't make cakes. If you do, you're probably better than me at making cakes. I don't think I've ever made a cake that I haven't had to cut the top off of, because it's just all over the place. But it's the same thing. And as I said, we will come back to it from time to time. Phase changes is one of the biggest ones. Here is a very simple slide. If you look at, imagine the little dots on here are atoms. As you increase in temperature, it forces them further and further apart. And as they move further and further apart, they become more gas-like as it goes through it. So as the energy increases, the distance between stuff increases as well. So for now, I'm just going to leave that as it is. Let you guys think of, or put that in the back of your mind. I'll call upon it later. Questions, though, before I move on? All right, that is the end of the chapter. So we've made it through the first chapter. Congratulations. We're making good headway now. Let me call up the second chapter. And in the second chapter, we're going to actually start telling the story of chemistry. So remember in the first chapter we were kind of all over the place, and I felt bad about that with our various topics and so forth. Once we get into the second chapter, it becomes a much more coercive story as we go through things. So what this chapter is going to do is it's really going to look at atoms and what atoms are made up of. And then how we know what they're made up of. So if I was to ask you guys, okay, we've all probably heard of atoms before. What is something about an atom? Anything at all to describe an atom?
If you split it, it will explode.
Okay, split it and it explodes.
It's the smallest unit particle of atom.
Smallest unit of an element. Okay, its definition. Anything else we know about atoms in general?
It has 3 parts to it.
3 parts to it, generally. As far as chemists are concerned, that's absolutely right. The physicist in me kind of wants to list the other ones, but no one cares. I'm half physicist, half chemist. Okay, so 3 parts of it.
Everything's made up of atoms.
Everything's made up of atoms. Okay, we have the periodic table of the elements to describe atoms and so forth. This chapter is really going to walk us through the science that explains all of that, the basics of it as we go through it. So when we talk about splitting of an atom, what are we actually splitting there? We're splitting the nucleus, and that is causing energy to be released. Okay? The smallest unit of an element tells us that it has the behavior of an element. Why does it have the behavior of the element? That's going to be talked about. The 3 particles that make up an atom are protons, electrons, and neutrons. We're going to talk about what those are and how we know what those are and so forth as we're going through things. But to start the story, we are actually going to go way backwards in time, and we are going to start with ancient Greece. Now, by no means is ancient Greece special in any way, shape, or form. Many cultures on the earth had very similar ideas to how matter is made up of. But just for example, the ancient Greeks believed that all matter around us was made up of 4 different components. And those 4 different components were combined together. Now this story in and of itself is not very different from the real, or our current understanding of what matter is. You would take these 4 things, you'd mix them together, and you would make various components. And you would take those components, mix them together, and make various things, and so forth and so on. So at the simplest form, the 4 basic units were fire, water, earth, and air. Really, those were almost uniform throughout the world for the basic components of what matter was made up of. You would combine them. So for example, if you took air and water, you would get moisture. Okay? If you took fire and air, it would be hot. Not really surprising, these are all things that you can actually interact with immediately. So if you took a pile of earth and you put it in the fire, when the fire went out, the earth was dry. So earth and fire made dry. If you took earth and you put water on it, apparently, I don't know, it got cold, and there's cold. Okay, let's say it's cold water as you're going through it. Opposite of fire, if you will. So it's not unusual to think, or at this time period even, it wasn't unusual to think of basic components making stuff up. But one of the fundamental things that ancient Greece had and discussed was whether or not you could separate things forever. So this was the idea of whether or not material could be separated forever. So if you had a pile of material, could you split it in half? And then take that half, split it in 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 half. And at some point in the future, would you reach some level to where you couldn't split it in half anymore? Okay, was there some fundamental unit, or could you keep splitting forever and ever and ever? And this is called continuous versus non-continuous matter. The ancient Greeks generally believed in what's called continuous matter, meaning you could split it forever. And it's not a surprise, because if you think about it with your eye, you could split it and 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 so forth. And they weren't doing actual experiments at this time. They were just thinking about it, and it made a lot of sense. So the idea of continuous matter was actually put forward by Plato and Aristotle. You may have heard of these people before. They're two of the most famous Greek philosophers of all time. And because of their fame and notoriety, this took off. Okay? So this was accepted as general knowledge in the time period that matter was continuous. So no matter how small you went, you basically never ended up with empty spaces there. Because you could always split it and split it and split it and so forth. On the flip side of this was, anyone want to try and pronounce his name?
Democritus.
There you go. We'll go with that. Democritus. That's probably what I would have said, kind of. I would have messed it up more. He believed that it wasn't continuous, meaning that there would be some small unit associated with the material that you couldn't go any smaller of then. And he sat and thought about it, and this made sense to him. Now, there's no way they could have done experiments at this time period. The idea of atoms and the size and so forth was well beyond their abilities. But he put forth the idea that there was something that was so small it couldn't be split anymore. He was not nearly as famous as the other two, because I can even pronounce the other two's name. So this thought, while it was recorded and so forth in history, did not win out overall. And it wasn't that it was just a short time period. Ancient Greece, what time period was ancient Greece roughly? Several hundred BC time period, okay, several hundred BC. These ideas would not really be challenged to any significant amount until about 800 or 1800 AD. So 2,000 years later. So Plato and Aristotle's idea of continuous matter would hold sway in the scientific community for the next 2,000 years. And the reason why it changed those 2,000 years later is because of the fact that we started doing experiments about it. Okay? We didn't just sit around thinking about it. We had the scientific ability and the instruments available to us to actually start doing experiments. So while the non-continuous idea was stamped out early on, it actually came back in force once we started doing experiments. So there are several different laws that were determined about this time period and help us understand atoms and what they do. There are three ones that we are going to talk about in this course. The first one is on the overhead here, and that is the law of definite proportions. So, law of definite proportions. And what the law of definite proportions says is that for any given compound, the components are always going to be the same. So it doesn't matter what the compound is. If you have that compound, let's say water, for example, if you have water, no matter where that water came from or how that water is made or anything along those lines, it's always going to be the same. It's always going to be 2 hydrogens and 1 oxygen. The same types of atoms making up your compound in the same ratio. Yeah?
I'm sorry, can you repeat that again? You said no matter what, it's always the same?
No matter where it's made or how it's made or anything like that, it's always going to have the same types of atoms and the proportion of atoms. And that's the definite part of it. So if you remember definite as like defining what it is, that's the idea where the name comes from. So that means that because it has the same types of atoms and the same ratios of them, it's going to have the same properties. And the properties of water really comes from the fact that it's made up of 2 hydrogens and 1 oxygen. If we change that in some way, so that it's no longer 2 hydrogens and 1 oxygen, it's 2 and 2, for example, we end up with this molecule here, which is 2 hydrogens and 2 oxygens. This is peroxide, hydrogen peroxide. Because we've changed something about it, that means it's a different compound. And because it's a different compound, it has different properties. So, for example, what is hydrogen peroxide used for?
Cleaning wounds.
Cuts, wounds, cleaning, right? Because it kills off the bacteria and so forth. If you were unfortunate enough to be a kid with a mom who liked using hydrogen peroxide, you know the sting of it. Okay, when it goes on and so forth. My mom used to use hydrogen peroxide a lot. Very different than water.
Yeah, hydrogen peroxide has been a while since I've used it. Is that the bubbles?
It does, actually.
What makes that bubble when it comes in contact with
So
blood?
what happens is it reverts back, it decomposes back to water, and as it does that, oxygen is released. And if the oxygen is released under liquid, then you get a bubble out of it. So what it actually is the decomposition of the peroxide to oxygen, and then that's being released out. So just by changing and adding one oxygen, you very greatly change the overall properties of it. Another example of this is carbon and oxygen. CO2 is carbon dioxide. What is carbon dioxide?
A gas that you expel.
The air we exhale is carbon dioxide. Okay. Relatively harmless. It's not really dangerous at all unless you're in an airtight room or something like that. Natural product of our bodies releasing energy and so forth, that's CO2. If we lose one of the oxygens and become CO, this is carbon monoxide. Anyone familiar with what carbon monoxide is? It will kill you. It's a poisonous gas. It builds up inside of houses and so forth when you burn fuels without a lot of oxygen present. So that's why you see carbon monoxide build up around furnaces and so forth if they're gas powered, because the gas goes in, and then if something's off about the ratio, you end up with carbon monoxide instead of carbon dioxide. My public service announcement for the day is if you do not have a carbon monoxide detector in your house, please get one. Okay? They're not super expensive. Some fire stations actually give them away certain days of the year if you're lucky enough to have one of those fire stations. But the reason is this. Carbon monoxide will kill you, okay, if it comes in a high enough concentration and you have no idea that it's happening. You can't smell it, you can't see it, you can't hear it. Nothing physically, no way can you interact with it until it's too late. Okay? You actually start feeling sleepy if it happens, apparently. I've thankfully never been in that situation, but that's what I'm told. So this is a deadly gas without any physical warning to it. So it's a good idea to get an alarm, and then what happens is if the concentration gets high, the alarm goes off, and then you know that you got a problem, and you call the people to help. So there you go. You can get them from just about any store. They sell them. Oftentimes they're built into the same thing as smoke detectors, so you get a carbon monoxide smoke detector at the same time. There you go. Okay, so that's carbon monoxide. Different from carbon dioxide by one oxygen, and by changing that oxygen, you greatly change the overall properties associated with it. Questions about that at all? So moving on to the next law. The first one was definite proportions. The next one is multiple. The law of multiple proportions. Now this really is related to the other law, except stated in a different way. In the other law, the definite proportions, it says that if you change the atomic makeup of something, then you have a different compound. What the law of multiple proportions says, it says that given elements can combine in different ratios. So no two elements can only combine, well, very few. Okay, let's start over. Elements don't always have to combine in the same ratio. This is something when I was learning chemistry, my dad had a lot of problems with. He said there's only 100 and some elements. If they combine together in pairings and so forth, you can only make so many combinations. Why would you want to study that? And that's the case here. That's not true because you can actually combine them in a lot of different ratios. So here's carbon monoxide, carbon dioxide. Iron and chlorine can actually form in about 6 different ratios with just 2 of them. Nitrogen and oxygen can form all of these relatively easily. So for any given 2 elements, you can have a lot of different ratios for the combinations. Each of these are going to lead to a different compound with different properties. And that's one of the reasons why we've got so many different materials in our lives, because we can combine these in different ratios from one another. So NO3, N2O3, N2O2, N2O4, they all are different ratios, and because they're different ratios, there are different properties associated with them. They may be closely related in terms of properties, but they will be different from one another. So this is the law of multiple proportions. Different atoms can combine in different ratios. Good with that one? Brings us to the last one, and this is the law of conservation of mass. I'm going to circle that one. This is the biggest one. Chemists, when they were working with atoms, one of the things that they noticed over time, and I'm all nervous about names now. Anyone speak French? What? Go with it? What? Okay, we'll go with that. He became very famous and very, very well known by doing experiments and carefully measuring things. Now, he had a few advantages that other scientists didn't. The biggest of which, and the reason why I chose this photo, is his wife. His wife was apparently spectacularly brilliant. Okay? Didn't get credit for a lot of the work, but turns out from the stories that I read that she was a huge, huge influence and helped him a lot in the work. The other thing is he had a very good job with the government, and he had money. And at the time period, the newest thing in scientific methodology that was out and about were balances. So we think of scales today. Many of us have scales in our bathrooms and so forth. You go to the science lab, we have a dozen scales up there and so forth. At the time period here, balances and scales were incredibly rare. If you're like antiques and stuff, you can look up photographs of old scales and so forth from when this time period. So think of this time period as roughly when Britain was colonizing the world and so forth, and how they packed up their scales and stuff because they were so expensive. It was incredibly rare for anyone to even have a balance or a scale or anything. He did, and he made good use of it. He did a whole series of experiments, many different experiments, and found that the mass of material you put into a chemical reaction is equal to the mass of the material that comes out of a chemical reaction. And he changed the masses of the material going in, and the product always changed the same way. So this is the law of conservation of mass. The mass going into a reaction has to be equal to the mass coming out of the reaction. This is the cornerstone of all chemistry. Everything we do in chemistry goes back to this law in one way or another. This even makes it into popular culture. The law of conservation of mass, the law of equivalent proportions. You hear it from time to time in a lot of different ways. Basically, what goes in has to be the same as what comes out. It may be hidden from you, such as making a mass into a gas or something like that, but it's still there. So if you have a log of firewood, you put it in the fire and it burns. Where does the mass go? You've got the ashes that are still there and so forth, but you also have a lot of the carbon of the wood being transformed into carbon dioxide and then going off into the air as a gas and so forth. So to do that correctly, you would have to capture that gas and mass it. This holds true for all chemistry except for nuclear chemistry. When you're dealing with splitting of atoms, the amount of energy that's associated there and so forth voids this law. It's the one time this law doesn't hold true. In terms of this class, we're going to assume basically it always holds true. And we'll talk about what that means when we get to the nuclear chemistry part. But that's the law of conservation of mass. Let me see if I've got questions about that? So the three laws I want to know, and we haven't really talked about like historical knowledge and so forth. I don't really care that you know who did it. I don't care that you know the time period that it was done or anything like that. What I do care about is that you know what the law says. So the law of definite proportion says that when atoms combine in certain ratios, you end up with specific compounds. Multiple proportion says that atoms can combine in different ratios to give you different compounds. And the law of conservation of mass says that the mass going into the reaction has to be equal to the mass coming out of the reaction. Do all those make sense? Yeah? Are those new to you? No? Yeah, no, okay. Most of you have seen those in one form or another before. And really, the reason why he could do the work is because he could afford the balances. There's nothing really special about it. You know, you buy the balances and so forth, and then you can do the work. So once we understand those laws a little bit, we can talk about Dalton's atomic theory. Dalton's atomic theory, I don't know, chemists say that it's the most important theory in terms of chemistry. I don't know if I necessarily agree with that, but it is useful in understanding how chemistry works. So if, for example, you buy a board game, and in that board game you've got the rules of the game there. You read through the rules, you understand the rules, everyone's playing by. These would be the basic rules of chemistry. The way that we're going through things. I am not going to ask you to recite back the 5 different things in any way, shape, or form. I may ask for one of them, or what one of them means, but I'll never just have you memorizing this just to recite it back or anything. But I am going to run through the ideas of Dalton's atomic theory. All of them we've actually talked about already. It's just kind of a summation of a lot of the different things we talked about and putting it together in one theory so it's easy to use. The first one, matter is comprised of extremely small particles. We're going to call them atoms. Matter is comprised of atoms. That's just the definition of chemistry and what atoms are. Okay, up to this point in the class, we've talked about that a lot. Number 2, atoms of a given element are identical. Atoms of different element differ from one another. So what we're saying here is that atoms of any element are the same, atoms of different elements are different. If you think about that, that's just kind of common sense. If an atom represents the behavior of an element, then 2 different atoms from different elements are going to be different from one another. And that's what this is saying. All it's saying is that the smallest unit of a given element is the same, which is not really surprising because it's the same element, and different elements are different from one another. So I don't think that's really earth-shattering. Atoms cannot be subdivided, created, or destroyed. Now, this is not exactly true because we already talked to, oh yeah.
That's why I asked you a question. So like when you
Yeah.
split it,
Mhm.
you're not destroying it. What are you doing to it then?
You are actually destroying it. Okay, now, bear with me a second here, okay? When this theory was put forth, nuclear chemistry didn't exist. We didn't have the ability to do nuclear chemistry and so forth. So at the time period where this was done, this was absolutely true. Now that we move forward 200 years, we have to put a little star by this and say, except in nuclear chemistry. Because when you split atoms themselves, you actually are dividing them. You're not really destroying them or creating them, you're actually dividing them. So if we think about a given atom, doesn't really matter what it is. Let's pick uranium. Uranium is number 92 on the periodic table there. It is commonly used in atomic weapons. Okay, so you guys may have heard of uranium and atomic energy and so forth. So let's say this is a uranium atom, and we split it. My handy dandy jagged line there, just split it apart. It breaks into two parts. Breaks into two parts. Now those two parts are actually other atoms of smaller ones. So we can say it changes into lead and, I'm just making it up, sodium. Lead and sodium. So when we have nuclear chemistry, we're taking atoms and actually splitting them into smaller atoms. Okay, that's called nuclear, we'll make sure I get this right. Nuclear fission. Okay, fission is where you're splitting them apart. You can also do the reverse, where you take two small ones and make them into a big one. That's fusion. You're fusing them together and so forth. So when this law was, or when this theory was made, it is actually true that atoms cannot be subdivided, created, or destroyed. However, since then, we've learned more science and we've updated it. That may actually be why it's called a theory and not a law, because we're still evolving it and making it a better explanation as we go through. But for purposes of this class, except when we're specifically talking about nuclear chemistry, this is going to be true. Atoms are not divided, created, or destroyed. Number 4, atoms of different elements can combine. Wait, before I move to say that. Number 3, the dividing and stuff. Everyone good with that for now? Yeah? Okay. I understand that that is not completely true and so forth, but I'm going to move on anyway. Number 4, atoms of different elements can combine in simple whole number ratios to form compounds. That just means that when atoms combine, it has to be whole atoms. You can't have 2.5 atoms of something going forward, because you can't have half of an atom, and so on. That's what the whole number means. And when different elements combine, they form compounds. So elements combine to form compounds. That's our definition of what compounds are. And the simple whole number part just means that you have to have whole atoms. You can't take a third of one atom, half of another atom, a quarter of another one, put it together, and make something new. It doesn't work that way. You have to have whole atoms to actually do stuff. And then 5, chemical reactions. Atoms are combined, separated, and rearranged. That, in essence, is the law of conservation of mass. When atoms go into your reaction, atoms come out of your reaction. That's what they're telling you there. And then they're simply rearranged as we're going through. So looking at them, number 1 is the definition of atoms. Number 2 is the relationship of atoms to elements. Number 3 is this idea of non-continuous matter. Remember the ancient Greek philosophy, non-continuous matter here. Number 4, different elements combined to form. That's the law of definite proportions and multiple proportions. And number 5, when you have a chemical reaction, things are rearranged and combined and so forth. That's the law of conservation of mass as we go through it. So none of these in and of themselves were unique. However, putting them all together makes it convenient, okay, to understand the basics that we're working with. Do all of those things make sense to you?
Question.
Yeah.
Will you ever ask if we can make the connection between those and Dalton's complication? Like, say, give an example,
I never have. I doubt it. I doubt it. I care more that you understand the basic ideas involved in those, not so much in the fact that they're even part of that or anything. Because going forward, we're going to use those and build upon them, and talk about why that is and so forth, but not like a reciting or tying, I don't think. I don't care about that. Yeah.
Okay, so if there was like a question or like a quiz or a test
Okay.
or whatever, and it was asking if an atom can be destroyed, would we just say it can't be destroyed due to the fact of Dalton's theory, or would we say, or would that even be a question?
Okay, yeah, that's a good question, but you're overthinking it. Number one, I would never ask. Well, I guess technically something could slip by me. I would try never to ask that.
Okay.
Because it's a technicality issue. There will be certain things, like in this course, hopefully this doesn't come as a surprise to you. Because of the level that the course that we're teaching, a lot of the things we teach you are not true in all circumstances.
Right.
Now, this is a prime example of that where we discuss, how and so forth. So I would try not to ask you that, at least not in that way or anything.
Okay.
I may say something like, why would Dalton's atomic theory have to be updated when you take into account nuclear chemistry?
Okay.
Something like that,
Okay.
but not what you're saying. If I ask what you're saying, can atoms be separated? Okay, I would have to accept both answers.
Right.
Because at this point, I'm telling you that they're both right.
Okay.
So anytime it comes down to a question like that, if you can make a good argument on why your answer is correct, and I can't just say that's not true, then I'm going to give you the points for it.
Okay.
There's been a few examples in the past of people have had crazy arguments with me about things where I said, yeah, okay. I would never have thought of it that way in a million years, but it's a good point. I'll give you the points for it, things like that. This would be one where I'd immediately give it over because of the fact that we've talked about it.
Okay.
The one I'm thinking of was, it was a question having to do with the metric system, and it was, what does centi mean? And what I was looking for was 1/100th of the base unit, because that's what centimeter is and so forth. But a student wrote 100, and his argument had to do with centipedes and so forth. And I'm like, I never would have thought of that in a million years, but I gave it to him in the end. It's not a big deal, but, centipedes have 100 legs, right? That's where the name comes from.
Yeah.
So yeah, okay, centi does mean 100 in that case. So, yeah, I'm not looking to be very strict in terms of those types of definitions and stuff. It's a process of it. Now, granted, I will say I get the last say, always. So, but yeah, it's usually not an issue. Okay, so does Dalton's atomic theory make sense for now? Really, a lot of chemists like to make students memorize things, probably the same ones that make you memorize the periodic table. I don't care about that. What I do care about, though, is that you guys understand these basic underlying principles here. What are atoms? What happens to atoms when we have reactions? And then when they form compounds, what does that mean as we go through it, especially in terms of properties? So, updates to the laws. Well, here we've already talked about these primarily. Nuclear reactions go against the law of conservation of mass, as well as the whole subdividing thing. Okay. We will discuss when it's important. We're going to do one chapter on nuclear chemistry because in today's society, that is really, really important. And I couldn't teach this class without talking about nuclear chemistry, nuclear weapons, nuclear power, things like that. Also, we say that atoms cannot be subdivided. That, you have to remember, is in the chemistry definition, they cannot be subdivided and have the same behavior as before. Atoms themselves can be broken down into protons, electrons, and neutrons. And we will do that in this class to understand why atoms behave the way they do. A gold atom acts like a gold atom because of the protons, electrons, and neutrons that are present. An aluminum atom acts like an aluminum atom for the same reason. So we do have to talk about those and how those build up to make your various atoms. You can go further down. Quarks, neutron, bosons, neutrinos, these types of things as well. We're not going to talk about those at all. Okay? If you've heard those terms in any way, shape, or form, good. I'm glad that you've been exposed to them. We are not going to use those in this course in any way, shape, or form, so we don't have to worry about those. And then finally, one of the laws says that atoms of a given element are the same. This is technically not true once we start talking about the number of neutrons involved in things. So 2 atoms of a given element can actually have a different number of neutrons, and those are called isotopes from one another. Isotopes will only become important when we are talking about nuclear chemistry in terms of behavior. Different isotopes have different behavior in terms of nuclear chemistry. The rest of the course, it really doesn't matter. So pretty much the first one and the third one are really limited to nuclear chemistry aspects of things. We will talk about isotopes because it'll make more sense when we get to it. Why? About protons, electrons, and neutrons. But there we are. So Newton's atomic theory has been updated along with the laws to a certain extent. Even though we still call them laws, we just added on to what that law is. Questions about that? No? Everyone still with me today? Yeah. I know laws can be kind of boring, especially one that says that when you mix things in different ratios, it makes different things. That's kind of common sense, and I understand that and so forth. But now that we've said it, we can move on and actually make use of it as we're going through it. So just here to wrap up, the atom, we are going to start talking about these atoms and when they combine in different ratios and form different things and so forth. But the first thing we have to understand is what an atom is and what the makeup of atoms are. So when we're talking about atoms and the size of atoms, it's really a limiting factor having to do with things. So the idea of atoms were in ancient Greece. Does anyone have any idea when we were first able to image atoms? Any clue at all? Okay, we were first able to image atoms about 40 years ago. The 1970s is the first time that we could actually do it. And the reason why is because they're so incredibly small. So here, for example, this is graphite. And if I show you what the graphite model looks like, on this end, you see the hexagonal arrangement of atoms going through there. If you look here, you see that arrangement. That's how I know it's graphite, by the way, because the arrangement there is going through it. So each one of the corners, there is an atom at. And believe it or not, this is an incredibly good image of atoms. This is really, really good in terms of what we can actually do. And the reason for that is because the distance between 2 points, or 2 bends in this, is 1.4 angstroms, which doesn't mean a lot to you, but it's like 1.4 times 10 to the minus 10th meters. So if you take a meter, well, the stick, and break it into 10 to the 10th segments, that's roughly how small that is. It's really, really hard to imagine what that would be. But because of the fact that it's so small, you can't see them with magnifying glasses or anything like that.
So how would you split the atom if they're so small?
Okay. So the way that you're going to split atoms is you're going to line them up to where you know where they are, put a whole bunch of them there, and then hit them with something and hope that you hit it. If you miss, no big deal. If you hit it, then you could actually split it as you're going through. So that's the way that we do it. We don't line them up one by one. Okay, so here, for example, let's take a look at the size of the atom. Now, this is not exactly made for it because it talks about cell size and so forth, but there we are. Images of various things, a coffee bean, sesame seed, a grain of sand, and I'm going to zoom in. There's our grain of sand blown up Going in a little bit further, skin cell, red blood cell. Here is probably the smallest thing that you would interact with in life, and that is yeast, like baking bread and so forth. We were talking about cakes before. Yeast. So if you've ever had a little package of yeast and looked inside of it, that's there. Okay.
Instant yeast?
Yeah, like instant yeast and so forth. Now, an atom is in here, but you can't even see it yet. There's no way that you can see it yet. So we're going to go in even further. Okay, here are viruses, the HIV virus. Down in here, we're starting to see the labels for atoms. Moving in. Here is glucose, hemoglobin, so these are part of the blood supply and so forth. Moving in even further. Okay. Here's water. Okay, so two hydrogens and an oxygen, and here is a carbon. Okay, so there's one carbon atom. So let's just zoom back out here a second. There's the things in the blood, viruses, cells, okay, getting to kind of real life things, grain of salt and so forth, and we're back there again. So when we're talking about size, a grain of salt we think of as a small thing. That is astronomically large compared to what an actual atom size is there in terms of that. So we can't think of atoms as going in and moving them and so forth. It doesn't work that way. We can't line them up to hit them with stuff. Okay, we've got to do other things about it. So next class period, what we're going to do is we're going to talk about 3 different experiments that scientists did to try and understand what makes up an atom. We can't even see them, but yet we're going to study what's inside of them. Yeah?
The first clippings due next class.
Yes, it is. Thank you for reminding me.
What we need to do for that.
Okay. So we're going to talk about that in next class, but the first thing we're going to do next class is talk about clippings. So what you're going to do is find a news article, whatever it is, science related, read the article and write a 1-page summary, 1 page being typed, summary about what it is. The first half is actually the summary, like talking about what the article is talking about. Then the second half is your personal response to it, just what did you think about it.